Okay, so it gives me great pleasure to introduce Elvira Maidomino from the University of Zaragoza. Go ahead, Elvira.
Thank you. Thank you very much, Peter. Thank you for inviting me to this seminar, which always has these many interesting talks, but I cannot say that at this time of the evening, I am always thinking about attending it in direct, live. But now that I know you have recordings, I'll go and check a few I missed in the last few months. So thank you. Let's see. I'm not sure I'll plan to speak for 1 hour. So what is the usual? The usual is like 45, 50
minutes.
Yeah, okay.
Yeah, whatever you want.
Okay.
We're flexible.
Okay.
Everybody should be muted but Elvira, so.
Okay, thank you. So I guess I can take questions anytime, but also at the end, whatever you prefer. So good. So let me talk about this point to set principle. So this idea of the point to set principle is an interesting way of using computability methods in geometric measure theory. So my plan today is to talk to you about this a little bit, and in particular, getting out of the Cantor space and getting out of our usual uniform metric measure. Okay. So let's see. Well, this is just the slide to show you that I'm going to talk about fractal geometry, fractal house of dimension, packing dimension, this kind of stuff. So everybody very quickly remembers that these are cases in which the dimension is naturally an integer value. Okay, and this is just a reminder of the definition of house of dimension. So you are in a metric space. That's all you need to have a dimension. But it's very clear very quickly that in order to get something interesting, you need to have a separable space. Okay, if you don't have a separability, then like dimension is always infinity in most interesting cases. So it really, even if house of dimension only requires a metric, actually what is requiring is a separable metric space. So you just need to define delta covers, which are covers with diameter at most delta. And then you define what is called S measure, S house of measure, which uses these delta covers and tries to look at the best delta cover. And the way you take into account that cover is by taking diameter of its element to the S. Okay, so this is where the parameter S comes in. And the house of dimension is the S in which this S house of measure radically moves from 0 to infinity. Okay, so the smallest S for which it is 0 or the biggest S for which it is infinity. Okay, and of course, sometimes you have a space in which dimension is infinity. That's not a very interesting case, but you can remedy this by changing the way you take into account the diameter in this house of measure. So, for instance, you consider, this doesn't right. Okay, that's right. Okay, so you have different what is called gauge functions that have two parameters, parameter S and the diameter, and they are alternatives to the usual diameter to the S. Okay. And well, of course, you may have seen this without the S parameter, and then you kind of trying to find like the right function for this. But in order to do dimension, allow me to consider gauge families, which are like functions with two arguments, S and the diameter. Okay, and again, the phi dimension, the dimension of E with gauge family phi is the infimum of all those S for which this S house of measure is 0. Okay, and they generalize. I don't know if you can see the button. You probably do. I don't, but I think it's because I have some message I cannot remove, but they generalize the usual case. We also have packing dimension, which is kind of the dual. Instead of coverings, now you have packings. Packings means that you have disjoint open balls, and they have diameter delta, and you're looking now at the supremum, okay? The biggest size of balls inside E, and this gives you P0S. That's still not a measure. You need to take an extra quantifier. You need to take countable unions and use and apply P0S to each of the elements of that union. But again, the packing dimension, once you get this using this extra quantifier, once you get PS, again, packing dimension is the S for which this PS radically changes the value. And it's, well, I won't say much more, but this is completely dual to Hausdorff dimension. And even if it doesn't look completely dual because of this line here, with the alternative characterizations, it is exactly a dual version of Hausdorff dimension, changing in the appropriate place lim sub and lim inf. Okay. Of course, in gauge dimension, you can also, in packing dimension, you can also change the way you account. So you value the diameter. So this is only one of the alternatives. You can have a different phi there and get phi packing dimension. Okay, so if you want to effectivize these kind of notions, let's start doing it in Cantor and Euclidean space. This is what most of you may have seen already. There are like several ways. You can use gambling. You can use these martingale or Gale definitions. And you can use the compression-decompression definition, which is related to Kolmogorov complexity, or yes, if you prefer, compression algorithms. At the level of semi-computability, which I will introduce next, you exactly are using the classical prefix Kolmogorov complexity. That, well, here is the, do you really see the last line of my slide? Let me see.
Yes, we do.
Oh, okay, great. Thank you. I am sharing the same mouse for both. Okay, apologies. Okay, so as you see, you have the usual Kolmogorov complexity for strings. Okay, the shortest description that gives you this string, and then you can look when looking at real numbers. It can be also interesting to look at the Kolmogorov complexity of a real number x at precision delta. Meaning I am looking for the shortest description of a rational number that is delta close to x. Okay, that's a very good way of defining Kolmogorov complexity of real numbers. You may be more used at looking at real numbers as infinite sequences and then looking at finite prefixes of those. But this definition is far more robust and is far easier to translate to other spaces. So this is why I'm using it here. And once you have this K of delta x, so remember Kolmogorov complexity of x at precision delta, then the constructive dimension or effective dimension, as most people usually call it, is just the ratio of K of delta x over a logarithm of 1 over delta. Okay, so for instance, if delta is 2 to the minus n, you would get the usual denominator of n. Okay, and if you take the lim inf when delta goes to 0, you get the effective dimension. And if you change this lim inf by lim sub, you would get a strong effective dimension. They can also be defined using gambling. And, well, I will not talk too much about the definition using gambling. I wrote it for some reason, but then time always goes faster than I think. So let's forget it for now, unless we need it later. So just these effectivizations, I will give you some ideas of why they effectivize dimension, but the point to set principle is really a definite argument, but I will get there. And they can all be relativized in the sense that Kolmogorov complexity can also be defined relative to an oracle A, and then you would get effective dimension relative to A or strong effective dimension relative to A. Okay, and as you have seen, I am defining effective dimension for reals, for points on the space. Okay, so this is still the space of Cantor or Euclidean. So if you want to define it for a set, in this case, for effective, you just take the supremum. Okay, so this is one of the advantages of being at the lower semi-computable level. Universalities exist and no problems there. This is slightly different when you try other levels of effectivization in which we have worked in the past, but I may not mention that so much. But this idea of being point-wise does not always happen at every resource bound level. I wanted just to tell you that. Okay, and I can also effectivize 5-gauge dimension. And what I do is I compare, again, the Kolmogorov complexity of X at precision delta, but I compare it with the corresponding gauge. Okay, so it's completely analogous to the case of phi of delta being delta to the S. Well, if you use a different gauge function, you're going to compare 2 to the K delta with, actually, you're going to look at the places where this equality holds. So the limit of 2 to the K delta times Phi(S) equals 0. Okay, so it's like you're looking at places where K delta of X and you compare K delta X with the minus logarithm of Phi(S) of delta. So you have then these effectivizations. How do they relate to the classical concepts? Well, we knowing interesting characterizations of both Hausdorff and packing dimension, it's very easy to see that Hausdorff dimension is upper bounded by effective dimension. Packing dimension is upper bounded by strong effective dimension. Okay, so well, this is useful. For a while, this was good enough. We were using these effectivizations to get useful upper bounds on classical dimension. We were looking at the cases in which they coincided. Okay, so for simple sets, for sets A within a certain level of the arithmetic complexity, actually you had equality. So effective dimension was enough to get the classical Hausdorff dimension or the packing dimension. They were called correspondence principles. I don't know why I have this less or equal. I'm sorry, I think that was a typo. It means equality, of course. It's always less or equal. This is equality. And well, it was also a very interesting way of looking at partial randomness. Okay, so this idea of each real number having an effective dimension value, that gave you, a non-trivial generalization of the idea of being Martin-Löw random, because this exact value could be any value from 0 to 1 was possible, and well, talking about exactly how random is real, in a way could be translated into which is the effective dimension of this. There was also, of course, a lot of quantitative analysis of sets. The smaller the set, the smaller the dimension, of course. That was pretty useful for complexity classes, for instance. And in that sense, there were other effectivizations, more strict relative effectivizations. Okay, well, this is okay. This is nice. So, well, you kind of sell it to the computability community. But then I think I consider a very good breakthrough these point-to-set principles that allow you to go back to fractal geometry, okay, to geometric measure theory, and you can have an exact characterization of classical half-dot dimension and classical packing dimension using effective dimension. Okay, so well, this has been around for a while, so you probably know them, but you can see that the way of getting this equivalence is using relativization. So for each oracle B, you have a different effective dimension dim to the B, sorry. And for each particular set A, there is an oracle that exactly gives you back a classical dimension. Okay, so it's a minimum. Okay, so that's a very interesting. There always exists for each set A, there is an oracle for which effective dimension relative to that oracle is classical dimension. And that happens too for a packing dimension. So actually, there's been quite a few interesting results have improving in fractal geometry using this point-to-set principle. I'll try to give you a small summary, but I also think that we still need to understand a bit more about this result, about the result itself, like, this minimum, this oracle that gives you back classical dimension. I think that's something that we want to know more about. I'll tell you a bit more in a moment of what people have done so far. So in terms of applications of this point-to-set principle, I particularly like Marstrand projection theorem. Okay, so Marstrand projection theorem was proven for analytic sets. So for analytic sets, the dimension of the projection of the set is related to the dimension of the set itself, at least for almost every direction of the projection. Okay, so for almost every direction, that is a measure one set of directions or angles. I don't know which are the more accurate the more used terminology. The dimension of the projection is the minimum over the dimension of the set and 1. And one of the very first applications of this point-to-set principle was a theorem by Neil Lutz and Don Stahl that extends this Marstrand projection theorem from analytic sets to sets for which packing dimension and half-dot dimension, they both coincide. Okay, so this proof is completely proven using a Kolmogorov complexity using effective dimension. There's been even a further result that I did not write. It's I don't know if it's written in the next slide, apologies, by Don Stahl this year, from May, I think. And what he has proven is an extension of both Marstrand's original result and the second result by Lutz and Stahl. And what he has proven is that for sets for which this point-to-set oracle B, okay, the oracle for which classical and effective dimension coincide, for the sets for which this oracle has a special property of being optimal in a very natural sense related to Kolmogorov complexity, then Marstrand's theorem holds. And these sets for which this optimal oracle exists, they include analytic sets, they include sets for which half-dot and packing dimension coincide, and others. So it's really a very, very beautiful result. And it takes us back to what I was trying to tell you, that I think we need to know more about who is this minimum, okay? Who is this minimum, this oracle for which you get a minimum effective dimension. So I think I have written, I don't know if I have the reference, otherwise I'll write it at the end. It's called Optimal Oracles for the Point-to-Set Principle, okay? And it's 2021 and it's in arXiv. Okay. Yeah, it was written here. I see it. Okay. So there are other applications. There's an intersection formula that was originally proven for Borel sets. And then Neil Lutz proved it for any set, actually. So he jumped from from a result that was only proven for Borel sets. Now it's known for every set. In this case, it has to do with the dimension of the intersection versus the dimension of the Cartesian product, blah, blah, blah. You can read it later if you're interested. There were quite a few more applications. I don't know, probably they are not all here, but for instance, Lutz and Stuhl have worked on Furstenberg sets. Ted Sleiman, I don't know if he's written this, but he had a very elegant proof on how the capacitability of dimension, that is the fact that the dimension of analytic sets is represented by their compact subsets, okay? So he proved that this doesn't happen for coanalytic sets, okay? And he proved it using the point-to-set principle. And recently also, Jack Lutz has worked on high-male bases, which are bases of the real numbers over the field of rational numbers. And he has built high-male bases of any positive house of dimension, again, using the point-to-set principle. So this is more or less like just the introduction of the point-to-set principle. Let me tell you a few more things regarding other spaces. So if instead of looking at real numbers, you want to look at any other separable space, for instance, how would you do the effectivization? Well, a very natural way of doing it is using a separator, a countable dense set, to kind of define information content. Okay, so it's, once you have seen this Kolmogorov complexity of a real number at a certain precision delta, well, it's just natural to think, okay, so it doesn't have to be using the rational numbers as like the coding of real numbers doesn't have to be done through rational. Any separable, any countable dense subset of the reals could be used in the place of the rational numbers. Of course, it could give you a different concept in principle. So, for instance, you may want to use, I don't know, of course, there are several choices that are clearly equivalent, like using dyadic numbers or using computable numbers, but you may think of more weird choices in which the concept of Kolmogorov complexity changes. But then once you use the point-to-set principle, you would again get classical dimensions. So it would give you alternative ways of getting to a classical Hausdorff packing dimension. So in any separable space, you kind of play the same trick. You define, you fix a countable dense set D, and you define a Kolmogorov complexity of an element of the space X at precision delta. Okay, so you just use at the smallest Kolmogorov complexity of W, where W is the coding of an element in D. D is countable, so actually you don't only fix D, but you also fix the enumeration of D. And so this is the simplest representation of the element X. Okay, what is not the simplest, but the simplest at precision delta. Okay, so it's just the same, exactly the same role as the rationals played in our past definition. But now you fix the D and you fix an enumeration of D. So once you have this, you clearly can define Kolmogorov, effective dimension, exactly in the same way as before, effective dimension and a strong effective dimension. Actually, the definition is just exactly the same. You just change that you are in a different space X now. And another extension that you can do is do it for a gauge dimension. Actually, what happened is that I think before this paper, dimension was defined always for the standard gauge function for the theta to the sort of delta to ds, and I think in this paper it was extended. Okay, so you have for any separable space, you define effective dimension and you define effective gauge dimension. Okay, so let me Okay, this is half time. Okay, I think I'm going a bit maybe too fast. So let me see. First thing we'd like to have is a point to set principle again. Okay, we want to be able to use effective dimension in other spaces and also with other gauge functions. If you change the gauge function, well, more or less things work in a standard way, except that very quickly you have to limit the gauge functions you use. For instance, here, I am using a prefix Kolmogorov complexity. Also because in this talk, I didn't intend to get very much into detail. But the thing is that the kind of gauge functions for which we are going to prove the point to set principle, they are not terribly large, okay? So because what happens is that in this effectivization of dimension, you're going to compare, I'm sorry, what did I do? I made, sorry, how do I do it? Sorry, okay, I can do this. For some reason, my screen was very small. Let's see if I can solve this. No. How do you do it? Okay. Help.
Can you go Control L or
Control L? Okay. Okay. Thank you so much. No, but the thing is that in my screen I see it full, but in Zoom, suddenly, wait. Okay. Let's try again. Okay. I don't know what I'm doing.
Maybe one of those buttons on the down there. Not that one, the next one over.
What I'm doing.
It's good anyway. We could read it, so go on.
Okay, wait. What I'm going to do is, okay, is this working now?
Okay. That's good enough.
Okay, thank you. Sorry, I don't know what I did, and you may be seeing it. I just thought you were seeing nothing. Okay, so as I was telling you, the thing is that if you're going to compare this delta precision Kolmogorov complexity with minus the logarithm of phi s, if I am correct. Okay, and the thing is that if phi s is very big, then you know the fact that you're using a prefix Kolmogorov complexity is going to be a problem. Okay, you may want to use plain Kolmogorov complexity instead. But really, the sort of gauge functions for which we have been able to prove the point to set principle are not that big. Okay, so we're going to restrict a little bit gauge functions. Some of the restrictions can be easily removed. But what I'm telling you is that, for instance, this last one here, this is what allows you to use a prefix Kolmogorov complexity instead of plain Kolmogorov complexity. This one is kind of similar. It's also kind of bounding how fast the phi grows, and this one is more just a useful way of being able to deal with limits, okay? In the same way that we are used to when dealing with dimensions, sometimes with randomness, we only look at 2 to the minus r limits. I mean, our limits are mostly represented by what happens with the sequence 2 to the minus r. For other phi gauge functions, you want to use a similar precision sequence. Okay, so this restriction is more like they cannot be terribly weird, but they can range over most values. But the last two ones are more related that they cannot be huge. Okay, so gauge functions, they always have to go to 0, etc., but they can do so extremely slowly. So in order to be able to do something useful with information theory, you need to bound a little bit. So using these limitations, as I tell you, you can be a slightly looser with those limitations. You can prove point to set principles again. Okay, so I call strong gauge families for families that fulfill those restrictions. So again, you get effective dimension and a strong effective dimension. And again, you have the minimum of the best of oracles. Okay, so there's at least one oracle that gives you exactly effective dimension equal classical dimension. So this is kind of the first nice things. Okay, as we expected, separable spaces are good enough to do effective dimension, and gauge functions, they mostly can also deal with point to set principles. Let's do something useful with this. Okay, so we're going to look at the hyperspace. So you know that for each separable metric space, you can look at the hyperspace, that is the set of non-empty compact subsets of the space, Kx, and you can get, again, a separable metric space on this K of x, on this hyperspace. This is usually called the hyperspace. You probably know. So in this metric space, you use Hausdorff metric, which is a way of measuring the difference between two sets. So you take the maximum over the distance of U from V, so the elements of U from V or the elements of V from U. And this gives you a Hausdorff metric. And this makes K of x a separable metric space too. And there's been some work done trying to relate the dimension of a space with the dimension of its hyperspace. Okay, so mainly by McClure in the 90s, he had several results trying to relate both Hausdorff and packing dimension for a set E and its corresponding hyperspace. Okay, so you take E as subset of X and KE the corresponding set of compact subsets of E. And he mostly do it for two cases, for self-similar cases and for sigma compact. What happens with self-similar sets, in case you don't know much about them, is, well, you probably do, but they are very well-behaving sets. For instance, they are very regular in the sense that packing and Hausdorff dimension, they coincide. Okay, so for instance, he proved a very clear relationship for sigma compact sets between the Hausdorff dimension of the set and the Hausdorff dimension of the hyperspace of that set. Of course, when you look at the hyperspace, you cannot keep using the same gauge function because you could get dimension infinity. Okay, so if you don't do anything in this space here, Kx has dimension infinity, and most subsets, most interesting subsets have dimension infinity. It's not very interesting, but you need to change the gauge function. So for instance, if you just are looking at the dimension with the usual gauge, so the basic gauge function, so the original definition of both Hausdorff and packing, then for the hyperspace, you need to use this gauge function, 2 to the minus 1 over Ts. So if the original was this one, in order to get some meaningful relationship between the dimension of the space and the hyperspace, you need to kind of change to this other one. And so in general, well, first we thought, okay, well, why do you do it only for phi s? For theta s, let's do it for any other gauge function. You can change for an interesting gauge function definition for x. So non-trivial, I mean, phi dimension for x to the hyperspace, you have the jump. Okay, so it's always, this is the jump. So you start with phi s for the space x, and in the hyperspace, you jump to 2 to the minus 1 over phi s. Okay, so McClure proved a certain relationship for sigma compact, and what he proved was that the packing dimension of the hyperspace is always lower bounded by the packing dimension of the set itself. Okay, I'm taking this result. There are a few other. The results for self-similar sets are better because self-similar sets are really far more restricted. But let me start with this one. So what we want to do is extend this result from sigma compact to as general as we can other sets. Okay. And our new tool is this point to set principle. You can now kind of look at for instance, the dimension of the hyperspace as the effective dimension of the hyperspace relative to a certain oracle. Okay, yes. Be aware that, of course, in the hyperspace, we are using a different metric and also a different gauge function. So let me tell you a little bit of how we do this. This was kind of my last thing I wanted to tell you today. So I'm going to be slightly shorter than expected, but I hope you'll pay me the same. So what we proved was for analytic sets. It's okay. So this is our generalization from sigma compact. All sigma compact sets are analytic to any analytic set. So what we prove is the same result. The dimension of the hyperspace, again with the jump of phi, is bounded by the dimension of the original set with gauge function phi. Okay, so what McClure proved was only for the basic gauge function. And how do you do it? Well, I'm not going to give you all the proof, but I like to show you where the point to set principle is critical. Okay. So by the point to set principle, once you fix the hyperspace and the gauge function there, you know that there is an oracle for which effective dimension is exactly classical dimension. So this oracle is fixed now. Okay. So how do you prove something like this lower bound? Well, you want to construct, your main goal is to construct points in here in KE, that is compact elements, those are the points of KE, points that have high Kolmogorov complexity. Okay, so you need to find an L in here, that is a compact subset of E, that has very high Kolmogorov complexity. Okay, remember that this Kolmogorov complexity is delta, the delta approximation of Kolmogorov complexity. Okay, so you need to use the Hausdorff metric. Okay, to find points in the separator that are difficult to describe and close to L. Okay. Okay. So what we do is we do it in stages. Okay. We construct a single compact set L, a single point in the hyperspace, but the construction goes by this for each precision delta, we do a step of the construction. Okay, and it is very important for us that we only need a strong dimension. That is, we only need to have high Kolmogorov complexity at infinitely many precision places. Okay, this allows us to do the construction like improving the L at each step. Okay, it's not very clear to us how we can do something like that that has a high Kolmogorov complexity at almost every place. Okay, the way you construct this compact set is very important here to be able to only think about infinitely many places. the second part is not so dependent on the point to set principle. What happens is that if you only look at compact sets, then the strong dimension of this set E, it's kind of very very close to what is called a box dimension. That is, in a way, it can be approximated in a very regular way. So you kind of see, since E is compact, for a compact E, you can very clearly cover E with very regular covers that allow you to use this box cover size for the to reach this high cover size for the hyperspace, okay, for the point in the hyperspace. Then, of course, since we were looking at analytic sets, this is where you use that the dimension of analytic sets can be very well represented by compact sets, compact subsets. Okay, so it's both for packing and for Hausdorff dimension. The dimension of analytic set is equal or very close. Well, it depends really on which result you need to the dimension of many of its compact subsets. At least there's one that represents the dimension of the analytic set. Okay, so somehow to kind of summarize, I mean, this is not the proof. The proof is far more than this, but I wanted to just to point out that the point to set principle allows you to only constructing I mean, you only have to look at a single oracle, and then it's just use a combinatorial argument to construct a high Kolmogorov complexity element of the hyperspace. Okay, and I wanted to finish with a couple of questions of things that we don't know yet. The first thing is, as you notice, the hyperspace dimension theorem is done for packing dimension. They are not very many results for Hausdorff dimension. I mean, the cases where you have results for Hausdorff dimension is because it does coincide with packing dimension. But I think there should be something doable once you have this point to set principle. There should be a way of connecting the dimension of the hyperspace, the Hausdorff dimension, and the dimension of the set in cases where, I mean, in cases that are non-trivially covered by the previous result. So this is kind of the main question would be, can you prove something for Hausdorff dimension using this point to set principle? Of course, it may not be the good direction to kind of try to mimic our packing dimension result, because I shall tell you the construction highly depends on the fact that this is packing dimension, but there may be other ways. And also kind of a new question suggested by Don Stoll's paper is, I think it could be interesting to find out, like in the cases where the oracle that you use that you get in the point to set principle, both for the hyperspace and for E. So like the oracle for which you are using this, or this for E. Okay, these two oracles, either one of them or both, if we assume that they have good properties, well, what kind of good properties? Of course, it could be complexity, but that would be probably too easy. That may not lead you very far. But things related to probably Kolmogorov complexity, you know, like how some optimality, just mimicking a Don paper. Could you get results, interesting results? Like, for instance, you know, if these oracles are nice behaving, then I get a hyperspace dimension theorem. And then this holds for the interesting cases, because that's what happens with Marstrand's projection theorem, okay? So for the cases where this oracle were optimal in some sense, then the Marshall's projection theorem holds. Well, here, I don't know if that would be that easy, but I think it could be interesting to try to distinguish, interesting cases for both A and B and see where that leads you, and see, for instance, like in the cases of analytic sets or other even more simple cases to start with, if they were included in this hypothesis of having very nice oracles. And I wrote the references here. Actually, this is the main paper. I wrote a couple of surveys, and I did intend to add, as I tell you, the paper I mentioned by Dan is optimal oracles for the point to set principle. Apologies, but I don't have the archive reference with me, but it's very easy to find. I think I'll stop here. Thank you very much for your attention. Please, if you have any question. Thank you.
Any questions for the speaker?
I have a couple questions. The first one is about the gauge functions just for like regular space, not for hyperspace. So you explained that for hyperspace, it really makes sense to use general gauge functions rather than just the exponential function. But do you have any non-trivial examples where the gauge function is useful for just Euclidean subset Euclidean space, for example, something like that?
Euclidean space. The thing is that Euclidean space, let's see, something interesting that has infinite dimension, but with the right H function doesn't. I don't know.
Okay.
Somebody help me.
So the typical example would be where the normal dimension is infinite, and now you want to get a better
that's it.
Unintended. Okay. And my other question is, so in this McClure result that you guys extended, it's an inequality. Is there a class of sets that you know of where the equality holds?
Okay, for these self-similar sets, you get equality both for Hausdorff and for Bakin. So they're extremely well behaved.
Oh, I see. Okay.
So if you have, sorry, I don't know where I wrote this. Yeah, so this theorem, here, sorry. This theorem, if you change sigma compat by self-similar, you get equality. And what happens with self-similar is that both for the set and for the hyperspace of that set, Bakin and Hausdorff dimension, they coincide.
I see. Is that the largest class that you know of where equality holds?
Largest, maybe. I mean, it depends. Compact sets also. So I guess compact set of self-similar, could be the largest that we know.
Okay. Thanks.
Thank you.
Any more questions? If not, let's thank the speaker again.
I think, does Peter have a question?
Yes, concerning the background, I'm puzzled about the name of the principle, point to set.
Okay.
What is the origin of that name?
I don't know if Jack and Neil are not around. I don't know why. Let's see, point to set. It's because somehow, effective dimension is pointwise. And classical dimension is, for points is trivial. Okay, so with 0. So maybe, but I'll ask them. I'm not completely sure. Yeah, point to set maybe because of that, because you get in some sort of characterization of the set, of the dimension of the set in terms of the dimension of the points.
And that is also related to the fact that you're using these approximations. Since
Yeah. Yeah.
otherwise, I don't see how it ever could work.
Yes. Somehow, yeah. I mean, yeah. There are other options on the Kolmogorov complexity, but like the approximation is hidden. You know, if you look at prefixes of an infinite sequence, in a way, you're approximating it because you approximated it always looking at delta 2 to the minus n. Okay, so instead of taking any delta going to 0, you take 2 to the minus the sequence 2 to the minus n, but that works the same.
Okay, thanks.
Thank you.
Okay, did I miss anybody else? I apologize, Peter.
That's okay. There is something in the chat. Oh no, yeah. Hello. Okay. Okay. Well, thank you very much. I hope
I'm going to stop.